Here's an example dealing with mechanical equilibrium, or we'll solve it with mechanical equilibrium. We have a 0.19 kilogram meter stick that's balanced on a fulcrum. So a fulcrum is just a place where something is supported up into the air, but it doesn't apply any torque. It's just the object can freely rotate around a fulcrum. And then we hang a 50-gram mass and a 200-gram mass on the left side of the meter stick, and the locations of those are shown on the picture. And then the first question is, where should we hang a 100-gram mass on the right side to balance the stick? So to answer this, we recognize that this is a mechanical equilibrium question. The object is not moving, so all of the forces and all of the torques must be balanced. So these three conditions would apply. The sum of the torques around any rotation axis must be 0. The sum of the forces in the x direction must be 0. And the sum of the forces in the y direction must be 0. So we're going to answer part A, or the first question, with the sum of the torques. All right, so I know all the torques around any rotation axis must be 0. Let's add this information to the picture. First, I need to pick a rotation axis. I'm going to pick the location of the center of mass, which is where the fulcrum is connected, is attached. So let's call that A. Right here. All right, so there's my rotation axis. Based on that rotation axis, I have 2 torques by the masses on the left and 1 torque by the mass on the right. Let's name those just for the purpose of our equations. Let's call this mass 1, mass 2, and mass 3. And I'm going to go ahead and draw those torques as well. So mass 1 and 2 create torques this way. So I'll draw 2 torques, one for 1 and the other one for 2. And then we have torque 3 this way. Okay, we know all of those must be balanced. All of those torques must add up to 0. Now there are 2 other forces involved. The fulcrum is holding the stick up right here. I'll call it a normal force, or you could call it the force by the fulcrum. And then the meter stick itself has a mass. So the force of gravity by the stick. However, neither one of those forces are causing a torque, because those 2 forces are applied right at the rotation axis A. So that means that the distance to the rotation axis is 0, and so the equation tells me that there's no torque. It comes out to 0. All right, let's go ahead and add the other forces here. I've got Fg1, I've got a bigger Fg2, and then this medium-sized one, Fg3. So I think everything's on the diagram. We could go ahead and show the distances as well. I'll tell you what, the diagram's so messy. We'll leave the distances R1, R2, and R3 off the diagram. All right, so let's go back to the equation. We're summing up all the torques. Torque 1 and 2 are counterclockwise, so they're positive. And torque 3 should be a negative. Make it negative. And all of those should add up to be 0. I calculate all the torques by R1, force 1, or Fg1, and sine of that angle. And then add that to R2, Fg2, sine theta 2, and minus R3, Fg3, sine theta 3. All of that comes out to be 0. Okay, I think the first simplification I'll make is all of my angles are 90 degrees. And the sine of 90 degrees is 1, so the sine pieces all become 1. All right, so now I have R1 times, let's go ahead and make FG mg. So that's going to be m1g plus R2, mass 2 times g, and minus R3, and mass 3 times g. So we're really there. We have all of the information to plug in there to solve for R3, which is what we were asked to find. I'll go ahead and make one more simplification. I can divide out the g. I know it's 9.8, but I'll just go ahead and divide it out. And so we'll be solving this for R3. R1 M1 plus R2 M2 and divided by M3. And we plug the numbers in there. I'll do that for clarity. So let's go below here. So R1 is all the way out from the rotation axis A. So that's 0.3. It's 0.15 plus 0.15. So 0.3 meters. And the mass is 50 grams. So that's actually 0.05. So let me see if I can fix that. 0.05. Okay, I hope you can read that. And we add that to distance 2, 0.15 meters. And that mass is 0.2 kilograms. And we divide all of that by M3, 0.1 kilograms. So I plug that into my calculator and I get 0.45 meters. So that's where we should hang that mass to make the stick balanced. In other words, so we can make the torque 0, the net torque 0. Let's try question 2. So again, it's a mechanical equilibrium. We're going to use one of the equations above. So we don't have any forces in the x direction, so we'll just do the y direction. So we have minus Fg1 minus Fg2 plus the normal minus the mass of the stick, so Fg for the stick, and minus Fg3. And all of those should be 0. So now we can solve this for n. So n is just really, it's the only one that's in the positive y direction. So it needs to equal all of these other ones. I'm going to make all the FGs mg. So M1, G, M2, G. The meter stick itself, so that's the mass of the stick, times G, and then M3G. So we have all those numbers, we're just going to plug them in. Mass 1 is 0.05 kilograms, and 9.8. And 200, or 0.2 kilograms times 9.8. And the mass of the stick is 0.19 times 9.8. And M3 was 100, so 0.1 kilograms times 9.8. All right, so there are all the numbers, and my calculator tells me that is 5.29 newtons. And that's the end of that problem.